So we are pleased to have Hakan Tureci from Zürich today to teach us something interesting about random lasers, in particular on diffusive variation.
Okay, so it's a great pleasure for me to be here and to contribute to this program. And I'd like to thank the organizers for this. So today, I'd like to tell you about lasing in diffusive random media. So an example of which you actually see here, it's a rendering of an actual lasing mode of this system, numerically calculated. That is a two-dimensional, what we call a two-dimensional diffusive random lasers, which is composed of sub-wavelength nanoparticles scattered in a disk-like gain medium, which is pumped from above with incoherent light. So I will get into these concepts in shortly. But I'd like to introduce random lasers in the context of a more general category of nonlinear wave systems, which I call here complex lasers. So other examples are wave chaotic lasers and photonic crystal defect cavity lasers, and I foresee that there will be other developments in the field as well. So shortly after introducing you, giving you a heads up about some basics of lasing, I will tell you about some of the recent experiments which have prompted us to look into this problem, some interesting results. And after sort of going over these open questions which have been lingering around for a while, I'll tell you about the theoretical framework that we have developed to address these kinds of questions, which is by now called ab initio self-consistent laser theory. And in the latter part of my talk, I'll give you some results in this context and then present the conclusions. So with the advent in nanofabrication capabilities, we have seen what started out in the 60s as a big box of a laser cavity being reduced and shrunk to sizes of the order of micrometers and nanometers. So this is an example of such a system. The length scale here is of the order of 1 micrometer and is a current realization of what we would call a Fabry-Perot type of laser. However, what nanofabrication has also made possible.
Fabry-Perot means with two.
Yeah, I will come to it actually. Just two mirrors. But what it has also enabled us is different confinement mechanisms for light. So one example is here a photonic crystal defect cavity by just removing one, let's say, one of these holes in a perfectly periodic structure, a random laser, which is the focus of this talk, and chaotic lasers, which are just non-integrable deformations of a dielectric cavity. So, but before going into these, I'd like to give you some, I'd like to remind you of some of the basics of laser physics so that we are on par with the terminology I'm using. So a laser consists of 3 parts. A resonator, which is here in the conventional geometry, is composed of 2 highly reflective mirrors, which confines light. A gain medium, which is here this blue blob here, which provides gain to the photons generated by incoherently pumping this gain medium with a broadband light source. And so this broadband light source is then converted into lasing photons, some oscillations at a number of frequencies. And the condition of lasing is when the total gain in the system is equal to the total loss. And in the rest of the talk, I will focus actually just on the resonator structure, while we keep the other other parts in the system, we'll simplify them to a great extent, and we'll focus on the complexities in the resonator. What the resonator does is, which I will, again, just for the sake of completeness, I will refer to the resonator part with the adjectives passive or linear in what's coming. So what the resonator does is it forms coherent feedback to the photons generated in the gain medium by stimulated emission. And this happens for this one-dimensional geometry at a discrete number of frequencies. And this is visible. For instance, if you look at the these frequencies become visible if you look at the scattering spectrum of light from such a geometry, where you will observe a number of very sharp peaks, which are equidistant in this case. And the conventional laser theory tells us that the lasing frequencies that will be observed will be a subset of the original passive cavity frequencies. Now, completely different beast is random laser. A random laser, which in the simplest realization here, is composed or is generated by just taking a beaker of dye solution, a gain medium, putting in a handful of nanoparticles in the sense that it is sub-wavelength, and then pumping it with an incoherent light source and looking at what's coming out. So, in general, what is observed, and this is an actual experiment which has been performed in '94. This experiment is the experiment which sort of started the modern field of random lasing. We started out as an idea by Letokov in late 60s. So here, what you observe is, as you increase the pump strength, the emission here, this is the spectrum in frequency, the emission here is pretty broad, while when you increase the pump strength, this broad spectrum narrows down, and if you plot the line width of this distribution as a function of the pump strength, then this line width collapses and remains at a certain minimal line width. Now, this particular experiment has caused a lot of debate because this line width, which is of the order of 4 nanometers in the optical range, this line width is not quite the line width that you would expect from a regular laser. It was much broader. So there was a debate whether one could really characterize this as lasing. And I think the final blow in this field, which started in '94, came in about '99 by Hui Kao, where she considered in this particular experiment zinc oxide nanorods, which are grown on a substrate, which have a sub-wavelength height, so that in z direction you have a simple confinement. But then in the xy plane, you have random scattering by these rods, which are randomly distributed. So these zinc oxide nanorods, they provide, in this case, gain as well as scattering. What she observed when she pumped this light with a pump beam from the top is that this typical broad fluorescent spectrum narrowed down dramatically. And then if she pumped it further, multiple peaks developed, which characterized what I would call multi-frequency lasing. And these lasing peaks were indeed very sharp, sub-nanometer, which tells you that this laser is no different from a typical laser. It's just analog information versus digital information. Once it's lasing, once you have put enough power into the system and it's lasing, it's as good a laser as a conventional laser cavity.
Here the rods are no longer nano.
These rods are still sub-micron. It's below wavelength, if I remember correctly. But there have been a number of...
0.2 nanometers.
Oh, no. So it's not the wavelength.
Oh, the width.
It's the width of
Oh,
the...
sorry.
Yeah.
Sorry.
Yes, it's the width. And I think the wavelength is around 500 nanometers, whereas the rods are sub 100 nanometer, I think. Okay, so, okay, I'm sorry to go through this again. Okay, so here are some of the observations which you draw out from the experiments which have been going on around this first observation. So if you consider such a system, which now is a view from top here, because Z dynamics in the Z plane is simple, and do scattering out of it, then if you look at the scattering spectrum, you wouldn't see any feature. It's so weakly scattering, the dielectric index mismatch between the rods and air is very little. So it's so weakly scattering that you don't see any feature in the scattering spectrum. So how does one associate the lasing peaks which arise to anything, to any property of the linear scattering medium? So this is one question that triggered our actual interest. And a second observation which came later and mostly actually in a very recent experiment is our experiments which looked at fluctuation properties of lasing emission. So typically these experiments are done by sending pulses, one after the other. And at each pulse, you observe the spectrum that is coming out. And two typical spectra are shown here. You might not be able to see this, but a black spectrum and a red dotted spectrum. And if you compare them, you will see that there are large fluctuations in intensity, whereas the laser frequencies are very insensitive to shot-to-shot excitation of the system. So the outcome is that, and this we thought, when we looked at this experiment, we thought this has to tell us something that's going in these lasers which is very strong. And indeed, it's a manifestation of strong mode-mode interactions in this medium, which I will come to later. But before this, I'd like to tell you about what I mean by resonances. So we are talking then about solutions of the Helmholtz equation, Maxwell equation, or in the stationary case, Helmholtz equation, where this index of refraction nx it defines a cavity, just like here. And then you look at scattering. You're sending plane waves at a real frequency k, which is continuous, and then observe the emission at a camera in the far field. And what you see, as you vary this real parameter k, is a sequence of sharp and broader peaks. Now, a mathematical definition of resonances is results when you assume that there's only an outgoing wave. So this is the two-dimensional case, the boundary condition, the two-dimensional case, and then you get only solutions which are at discrete and complex frequencies. And the real part and imagine, so here's the distribution of them in the complex plane, in the lower half plane. And the real part of these frequencies denotes the frequency, and the imaginary part denotes the sort of the decay rate of these modes. So as you see here, of course, it's well known that these two things really superpose. This calculation was actually done for the same cavity, really. And these sharp peaks are obtained whenever you have one of these resonances coming very close to the real axis. When the resonance has a very small imaginary part. Now, the typical picture of lasing is that you provide gain into the system, which makes up for the loss due to leakage of this mode. And so the leakage rate is proportional to the distance from the real axis of one of these resonances. And then the idea is that the gain then pulls up these modes onto the real axis. And then the lasing modes are in one-to-one correspondence with these resonances. Now, this works well for systems which are very close to being closed, very highly reflective, high Q cavities. There are major problems with this kind of thinking. One is that this kind of picture neglects mode-mode interactions. When there are several modes lasing, they affect each other via what's called a spatial hole burning. It's just a nonlinear interaction. I will come to this. And however, another more serious difficulty is that when you keep increasing the pump, then these actually pass the real axis and become exponentially amplifying modes. And we know this is not possible. So at some point, gain saturates, and you will have at the end oscillations at the real frequency. But there are also mathematical problems with, for instance, using these resonant modes in an expansion of the electric field of the lasing field at a typical pump power. One of them is that these resonances are known to be not orthogonal.
You mean the corresponding?
The corresponding resonant modes, if you want to do an expansion. And there are ways to get around this. But there's really no practical way that we found out by looking into this as our first starting point to do this for a non-separable complex geometry. There's no well-defined prescription for this. But a more serious difficulty is that these modes here in space, they actually diverge as you go to infinity, exponentially. And this is a serious problem because typically you observe with a camera what is coming out of a laser, and there it's not giving, these modes don't give you a good description. So this prompted us to reconsider the lasing problem from going back to the original starting point and see what we can do in a consistent manner to treat very open geometries, very leaky geometries. So I will assume that you're not very familiar with what's called the Maxwell-Bloch equations. I will shortly introduce it here. So it's just the first equation on top is just the wave equation with a nonlinear polarization term. So I'm considering such a geometry here, where this nonlinear polarization is generated by distribution of two-level systems that are uniformly distributed in the cavity. And they are described, the polarization has to be described then together with the inversion. So these are just the off-diagonal and diagonal elements of the atomic medium density matrix. So, and the most important parameter here is this pumping term, D0, which tells you about the pump that you are using to generate inversion. So D0 is at your disposal. You can change this. And then you generate an inversion, which here then generates a polarization via the electric field.
So it's a nonlinear system of equations.
These are a nonlinear set of partial differential equations. And then this polarization appears here and then derives the electric field, which in turn enters in the other equations. So
probably you can consider it linear for finding these modes.
So that's what I will actually address in the later parts of my talk. But let's then you would like to expand the electric field somehow, and this is possible if the cavity is very closed. You can then approximate the modes or resonant modes of the system by an equivalent set of modes for a closed counterpart of the system. But when the geometry is open, this is not possible. So what
In what sense is this semi-classical?
Semi-classical in the sense that you neglect the quantum fluctuations of light. So you're looking at the mean field solution of the photonic system.
So when it's justified, basically?
That is justified when the number of photons in this mean field is large, so that it's justified that you are in the mean field. It's not justified when you're in the quantum optical regime where you have only few photons and the fluctuations that are in the mean field are large. But this is the same set of equations now. I'm writing these equations for the envelope of the electric and the polarization, which are known to oscillate around the atomic frequency. So the gain medium, it's the same equation before.
Basically, it's Fourier.
Yeah, so I've extracted a fast oscillation at omega A for the electric field and polarization. It's not important. I will come to it because we will never come back to these equations again. So the ansatz that we propose is very general. We assume that at the end, when steady state is reached, you have excited the system, the steady state is reached, the electric field is oscillating at a discrete number of frequencies. This is equivalent to saying that the spectrum consists of sharp peaks. And the coefficients of this discrete Fourier series are what I will call now nonlinear modes of the system, nonlinear lasing modes of the system. So here's no reference yet to the underlying linear wave system. So both psi and this laser frequency denoted by capital omega mu, as well as the number of such modes in the sum are not known and are functions of this pump strength d0. So when you insert this ansatz into it and play with the equations, you will find that a little bit complicated looking beast, but in essence it's very simple. On the left-hand side, you have a Schrödinger-like parabolic operator for the electric field. It's now not wave operator because we have extracted this fast oscillation and looking at the envelope. So it's a Schrödinger-like operator with a Laplacian here. And then on the right-hand side, you have a complicated looking expression in space, but its time behavior is very simple. It's oscillating at a harmonic set of frequencies. So I will just represent it as a sum over such harmonic oscillations. Now, this spatial dependence of this distribution of this of these sources are in turn dependent on the electric field. But for now, let's assume this is a distribution. Then we can just get the solution by just using the Green's function of the operator, linear operator, on the left-hand side of the Schrödinger operator.
But it's a non-linear problem. It's self-consistent.
But yes, and this, now if you do this, you obtain a set of equations for these nonlinear wave amplitudes via the Green's function of the linear operator and the resulting nonlinear set of integral equations. Now, looking into this system, what you see is that that D0 plays a prominent role. It's the pump strength that you put into the system. And then you have the Green's function acting on a source distribution. You can think of this as D0 times psi nu over 1 plus a sum over these lasing modes in the system. So, and this denominator here, the saturating denominator here, represents the modal interactions between the modes when several of them are lasing. And this Green's function then is able to connect it to the mode itself.
So if you just neglected this term in denominator beyond 1,
yes,
you get linear.
Yes, and this is the first thing we do to get some insight into the problem. But things you will see that in the full nonlinear regime change very much. So just let's consider this as a set of equations on their own. What do we observe? So first of all, the laser frequency and the psi nu, these are unknowns. So you have a vector of functions on the on the left-hand side. So and laser frequency appears explicitly here as well as implicitly in the Green's function. Psi nu equals 0, a set of psi nu's equal to 0 is a solution, is a trivial solution. As D0 is very small, is in epsilon vicinity of 0, there's no other solution to this equation. When you increase this strength D0, then a non-trivial solution emerges via bifurcation. It's known to be Hopf bifurcation for the simplest case. And then this lasing mode, one single laser mode which has appeared, is now goes into the denominator. and begins to suppress upcoming modes which are trying to laze. And so this non-zero first mode competes, that is turned on here, and suppresses the higher modes which are trying to laze, which happens at a set of thresholds, higher thresholds, starting with the first one. So that's sort of how what this equation tells us. So the most crucial ingredient in this nonlinear equation is the Green's function, which gives you the response of the linear scattering system. And here is the departure from the conventional thinking. So what are we looking at? We are assuming that once lasing is reached and we are in the steady state, we have a source at x prime, let's say, or distributed over the cavity, which is oscillating at capital omega. This is set by the laser frequency, which we don't know yet, so I will assume it to be a parameter. And then you would like to ask the question of what the electric field will be at x, excited by the system when it has reached the steady state. So this electric field is nothing but the Green's function of the system. And you can write a spectral representation of it, which contains resonant modes, as well as its resonant frequencies, omega m, which are complex. But one important thing one should notice is that when the system has reached steady state, everything will be oscillating at this pulsing frequency of the system, so at capital omega. Because we have free space here, the oscillation at infinity, the spatial oscillation at infinity has to oscillate at this frequency as well, capital omega. So we have a parametric boundary condition which is dependent on your dipole source frequency. Therefore, this Green's function has to contain modes which are parametrically dependent on this source frequency, and the resonant frequencies are also parametrically dependent on this source frequency omega. It's a little bit interesting situation because normally Green's function allows you to distance yourself from the source. It tells you about the natural response of the system. But it turns out here, when steady state is reached, you have to, the source frequency, which is real, has to be in the description and in the Green's function.
Because of this specific boundary condition.
Because of the specific boundary condition and the condition that everything is oscillating at the source frequency at steady state. It's a linear problem in that sense, in time domain. So when you look at the problem, you see that there's this just tells you that there's a flux which is established when steady state is reached, a steady state flux, and this represents a non-Hermitian boundary condition, such a parametric boundary condition. And then usual development of non-Hermitian mathematics follows, and it turns out that you have to expand this Green's function, also use in terms of the adjoint partner of these modes. And orthogonality relation is replaced by a bi-orthogonality relation, etc. But the nice thing is that this orthogonality relation can be expressed within the compact domain of what we call the cavity. So although the problem is in the infinite domain, we can express this condition right on the boundary. After this abstraction, let me just give you a concrete example. Let's consider a one-dimensional system with a mirror on the perfectly reflecting mirror on the left-hand side, and the dielectric step index on the right-hand side at x equals a, and the radiation flows to infinity. If you solve it with this parametric boundary condition, what you get is again trigonometric functions for the inside, and for the outside, again a trigonometric oscillation, but at the source frequency capital omega. So if you plot these modes, then you find that these modes in the cavity are amplifying towards the boundary and are oscillating constantly outside. Whereas resonances, what you would call resonances or quasi-modes or quasi-bound modes, they actually explode at infinity. So as an example of this parametric dependence that I told you about, let's consider solutions the constant, so these modes we have come to refer to as constant flux modes because they represent a constant flux towards infinity, a constant current. And so in this case, this is the imaginary, the complex plane, and I've set the oscillation frequency capital omega onto the real axis here, so it's about 19.5. And then the solutions that you obtain in this range are these complex frequencies in the lower half plane. If you change this frequency here, then you get another set of solutions. If you change it further, another set. If you let it flow, you find that there's an analytic flow of these frequencies. And this enables us to identify each of these modes as being one mode, whose properties change parametrically dependent on the oscillator that is exciting it. So these CF modes are just indeed different from resonances, and it's visible here. If you plot the CF modes versus the distribution of quasi-bound modes or resonances, the resonances in this case have a complex, have a constant imaginary part in frequency. So these circles, and the constant flux modes only coincide with these CF modes when this exciting frequency is close to one of these resonances. Otherwise, they don't coincide. So what do we do with this information now? So we have armed ourselves with all the information about the linear part. So the thing is, we would like to get some results. We would like to actually truncate this Green's function, this sum, infinite sum. And we do this, there are two distinct situations in this truncation that can arise. One is when this oscillation frequency capital omega, which we don't know yet, on the real axis has only one of these CF poles that is very close to it, but the others are far away from it. That's what's called a low finesse, high finesse situation. It corresponds to a very highly reflective cavity, just like the Fabry-Perot cavity at the beginning. Then you can truncate this expansion, and then to be consistent, you have to also expand this nonlinear mode in terms of a single constant flux mode. And this amplitude tells you the intensity of it when you turn on the gain. So this reproduces standard multimode lasing theory, except that via this denominator, we take into account the nonlinear interactions to infinite order. It's not for small intensities, but large intensities as well. However, a more interesting situation arises when you cannot really distinguish these constant flux modes in terms of its contribution to the sum. That's a typically low finesse situation. It's when you don't have mirrors, for instance, in a random laser, very weakly scattering random laser, so that a number of modes contribute here. Then to be consistent, you have to expand this nonlinear mode in terms of a set of CF modes, which tells us that a nonlinear mode of a single laser frequency can be composed of several CF modes of the cold cavity, which is no wonder, because after all, when you turn on gain and there are other lasing modes, you have an interacting system. It's no more the system that you had previously. But this is something new in terms of conventional thinking in laser theory. So how do we go about solving this equation? So here in the rest of my talk, I'll just present you an example that actually a realistic example that we have picked. It's a gain medium which is in a disk, a gain medium in a disk, which contains delta function scatterers, which are very weak. So once you put radiation into this system, it flows immediately out, diffuses out. The first thing you do is you linearize, assuming that you're very close to the first threshold. And then when you expand it in terms of constant flux modes, CF modes, in a set of CF modes, then you get an equation for the coefficients AM. These coefficients AM live in a complex vector space. And you get an equation where the pump strength D0, which has to be real, appears inversely here as an inverse eigen value of this operator T. And this operator T is this integral over CF modes, which are, and its adjoint, weighted by the index of refraction distribution in the medium. And typically it's non-Hermitian. So you don't, typically the eigenvalues of this T operator are complex, lambda mu's are complex. So in order, something special has to happen in order to get a real value. And that comes about by seeing that this T operator is actually a function of this parametric frequency omega, which is the frequency of the steady-state oscillations that are reached at the end, the laser frequency. So typically what you do is you let this omega flow, and the eigenvalues, which are n in number, let's say, they flow. And each of these eigenvalues hit the real axis at some point of omega. So that particular omega is the laser frequency for which this one of the eigenvalues is real. And the inverse of this real eigenvalue are the thresholds that you get. So you get a number of thresholds. However, only the smallest of them is the actual threshold. The others represent thresholds of the modes, the other modes, based on their lifetimes, let's say, which neglects mode interactions because of this denominator here.
So they never actually realize.
You would expect they would be closely realized. I mean, because these interactions you would expect might be not that strong, which was the assumption prior to this work. But it turns out destroys all the linear picture, and we can follow how this destruction is happening. So just want to point out one thing in terms of random matrix treatment of this operator here, non-Hermitian operator. The lasing frequency is not an eigenvalue of this operator. It's a parameter in this operator which makes its eigenvalue real. I will come back to it. So one thing is that these CF modes have a very narrow distribution in this for this type of geometry in its imaginary in its lifetime. So most of them have similar lifetimes, and this reflects on the thresholds being distributed very close to each other. So all of these modes are trying to turn on at the same time, and they are very sensitive to small fluctuations in the pump power. So just now the full solution in what's called the single mode regime, when you increase this pump parameter D0 and look at the actual nonlinear solutions of this system, full solution, and plot the intensity, which we define by the sum over amplitude squares of the expansion in the CF mode space, then you find that all solutions flow to 0 until this first threshold that is determined by this linearized theory. That is exact. And then you get a non-remarkable increase, monotonic increase. But the interesting thing is, if you look at the decomposition of this lasing mode on the CF mode basis, when you look at the amplitude distribution very near the threshold, you find that among these modes, only one of them is 99% determining this mode. So it's very close to the linear mode at the beginning. But when you increase the pump power, you find that power is distributed in other linear modes as well. And at the highest pump power here, you find that 60% of the power is actually carried in these sidebands. So here's a typical solution, the nonlinear mode, and its expansion in a series of CF modes. 33% carried by this, 12% carried by this, etc. And there's a big entropy in general at high pump powers. One important property that one observes is that these modes, lasing modes, peak at the gain boundary. And this they inherit from their constant flux components. each of these constant flux modes, they peak at the boundary, and this is no different than this mode peaking at the boundary for this one-dimensional open resonator. And there's a physical interpretation for it, which I will not get into. Now, in most important regime, multimode regime. So now we solve the full equations. This was the threshold that we determined by linearizing the theory. And indeed, first mode turns on them. The higher thresholds are denoted in this D0 are denoted by these arrows obtained from the linearized theory. Now, what you find when you solve this problem is that the second mode turns on all the way here, while you expect these many modes to turn on in this interval of the order of 8 modes. So when you reach this point, you have only 1, 2, 3, 4, 5 modes lasing, although you started out with 16 modes in this case, I think. So there's a so these are the nonlinear lasing modes at the highest pump power. So it turns out that there's a big modification in the thresholds that you expect of these lasing thresholds. This you can quantify by drawing a diagram like this. So in this here, I plot the threshold that is obtained for each of these modes. The lower value of this bar for a given mode here tells you the lower value here tells you the threshold that you expect based on linearized theory, no interactions. The upper end tells you when it actually turns on, the threshold, the nonlinear threshold. So you find that there's actually almost 100% change in the thresholds for these modes. So nonlinear interactions are very, very strong in diffusive random lasers. So this kind of strong reduction in expected number of lasing modes tells you that there might be a band, there might be an upper limit of number of possible lasing modes that are lasing in a system like this. Another observation is that if you plot the actual laser frequencies as a function of the pump power now, we have plotted the intensity variation as a function of pump power. We see that the laser frequencies are quite stable with pump power. They don't change much. However, this situation is only particular to this instant. Another generic situation is shown here. Here, I'm plotting, again, the same kind of multimode situation for another configuration of scatterers as a function of pump strength D0 again. You find that there's a very strong non-monotonic behavior. Intensity doesn't just keep increasing for each of these modes as you increase this pumping strength D0. You see that one mode here actually turns off after it starts lasing. Now, these are the laser frequencies of these modes that I plot, and I want you to focus on here. So what happens is where this turns off, there's some kind of interaction between this black mode and this one here, whose laser frequencies are plotted here. So they come close to each other as pump strength is increased. When the laser frequencies come close to each other, they begin to interact very strongly, and then one of them turns off. You can then show that the remaining laser mode has a kink in input power, and it actually inherits the identity of the mode that is turned off, which seems to be seems to be related to what's called synchronization in nonlinear oscillator systems. So two laser frequencies, two nonlinear oscillators which oscillate, come close together, and then one disappears, and you have a synchronization oscillation at a single frequency. So these kinds of disappearance of frequencies are very interesting and stand very much in contrast to the mode density for the linear problem, for instance. Now, the role of the fluctuations. Fine, this is the last slide, I think, or maybe the last two. So here, this is the intensity evolution for the distribution that I've first shown you. Then we consider a second situation where we let the pump light, which is actually uniformly impinging on this disk, let it fluctuate a little. Put a white noise on it. This is denoted by this dx here. keeping the power same, which is coming in.
Function of x.
Yes. So the pump is now fluctuating from one point to another. There can be various reasons for it. Now solving the system again, you find that the intensity evolution is very different from before. Better realized if you look at the spectrum in this final pump power, the 115. The laser spectrum shows that between the modes of these two sets are very different, can be very different in terms of its intensity, but the laser frequencies are very close for these two configurations. So which just relates directly to the experimentally observed spectral variation or spectral fluctuations. In retrospect, what this tells us is that pump fluctuations in the system probe the sensitiveness of the thresholds. So because all these modes, as I told you, have thresholds which are very close to each other, they try to turn on at the same time. But a little variation in the spatial distribution of the pump power can prefer one with respect to the other. And once the order has been exchanged, one is turned off on before the other, the variation, which is very strongly dependent on the interactions now, can be very different. And so in that sense, there's some kind of extreme sensitivity to the pump fluctuations in the system, which reflects a basic property of the system: its openness, leakage, and its strong interactions. So final remarks. The understanding of steady-state lasing requires the introduction of proper modes of an open system that is driven harmonically by an dipole, which we call the CF states, CF modes, which are non-Hermitian. The linearized theory predicts thresholds, laser frequencies, etc., at least the first guesses, but the later evolution, when modes have turned on, are strongly dependent on actually being able to follow what modes actually are turning on. And so there's actually some probably interesting connection to non-Hermitian random matrix theories that have been developed in the past, which have been actually sitting on rather abstract mathematical grounds. But here we have an actual realization of such boundary condition, and would like to understand how you understand the fluctuation properties of the linear system. Mode competition, turns out, pushes out higher thresholds, very strong push out, and can modify even the expected lasing order. And the extreme diffusive regime of a random laser is characterized by strong intensity fluctuations, while laser frequencies are relatively stable, turn out. And I'd like to thank my collaborators, Doug Stone at Yale and his group, and Stefan Rota, who is now in Technical University of Vienna. And here are some references which are related to this work. Thank you for your attention.
You get what you mean by the extreme diffusive regime.
Extreme diffusive. So these subwavelength particles, they have a dielectric index of refraction, which tells us about their scattering strength, which on an impinging light. So this index mismatch with respect to the background is very small. So light basically gets reflected very little from these scattering particles. That's extreme diffusive regime. I mean, another way
of individual scatter, right?
Yes.
So it's multiple scattering.
It's multiple scattering with this basic assumption.
What happens if you increase this contrast? I mean,
yes. So then we find that you get localized modes. So you have to realize earlier the thinking was that you would get actually in this extreme diffusive regime modes which would be uniformly distributed all over the system. We find here that they are actually distributed on a ring at the gain boundary. So that's one thing. And if you enter the strong scattering regime, then you find actually modes which are localized in the interior of the system, and their threshold distribution is markedly different from what you would get for this kind of weak scattering regime. And we are now looking into being able to distinguish an Anderson localized laser from a diffusive random laser by just looking at intensity, by looking at fluctuation properties of the observables like laser frequency, intensity, fluctuations.
Can you
etc.
experimentally realize?
The problem is only recently people have begun to do systematic experiments. Earlier experiments were very unsystematic. And now, for instance, this recent experiment with fluctuations, that has only been possible in the past year. Now I'm talking to people from Nice and Paris, and they have now lasers for which they can actually make these experiments very systematically.
What determines the perimeter of that lasing regime? What determines the high gain regime?
The
high gain regime. You claim that there is some perimeter of this cavity that gets generated.
Yeah.
It's a real cavity or
No.
it
No.
is a fluctuation.
Yes, so so it turns out this boundary is purely determined by the pump beam that you are applying. So, and this has been observed in experiments and people didn't understand it. So,
How is it related to the beam exactly geometrically? Where is it? Is it something that is just determined by the beam or
by the beam,
Just
by
the
the
beam.
beam. So you take one of these nanorod system and you shine the beam, and the beam, the Gaussian beam, determines your boundary, basically. And this is, which means to say that everything, all the radiation generated in this disk gets gain, is amplified. So you find that this effective cavity, which is determined by just the pump beam, actually determines also the average laser frequency spectrum, average mean spectral range, free spectral range, yes, frequency spacing.
So let me see how you understand intuitively. Intuitively, this formalism basically says that you will change the index of refraction. The index of refraction will trap the beam, and you will get something like, similar like to a soliton. That is the same mechanism similar to the one that generates solitons?
So in a way, we have a vector nonlinear Schrödinger equation, where the nonlinearity is a little bit different. That's what we effectively are solving. And yes, I would say that it looks like actually a soliton solution of the nonlinear Schrödinger equation with a gain, with a saturating gain though, not quadratic, but a saturating gain.
And the location, it depends, but it is determined by the beam and the fluctuation in the random potential.
Yes,
For
exactly.
example, if you have the same beam, but you change the realization, it will be somewhere else.
The laser frequencies will be different, the modes will look different, etc. Yes. That's another mode of probing the fluctuations of the system. I presented you fluctuations in the pump beam. You could also think of changing the realization of scattering disorder, which would then affect only the laser frequencies, which I've shown you are actually less immune to pump fluctuations.
More questions? Not later. Thank you.